In this video, we're going to review how to solve linear circuits, and we'll relate those techniques to a matrix representation of a linear circuit. We're going to start off with an exercise. Pause the video and try to calculate I2 for this circuit in 3 different ways. One way you could have calculated I2 is to use Kirchhoff's voltage law, abbreviated KVL, as a starting point. There are several variations on this theme, but we can imagine drawing a KVL loop around the left mesh of this circuit to find our first equation. V is equal to IR1 plus I2R2. V is equal to I1R1 plus I2R2. Then we can use Kirchhoff's current law, abbreviated KCL, to express I1 in terms of I2 and I, because those 3 currents add together at node V2. So we know that I3 is equal to I, and it and I1 add together at node V2 to create I2. Finally, we do some algebra to arrive at a solution. Another way uses Kirchhoff's current law as a starting point. We write the currents adding together at node 2 in terms of voltages on the adjacent nodes. So I1 is given by V minus V2 divided by R1, for instance, which gives an equation in 2 unknowns right away. Then we can rearrange that equation by cross-multiplying R1, and finally arrive at the same answer that we found using KVL. The third way I thought of was using superposition, which is a technique that's always seemed a little magical to me. We draw 2 superposition subcircuits, calculate I2 in each of them, and then add the superposition subcurrents to find the final value of I2. As a reminder, we drew the superposition subcircuits by zeroing out all but one power source in each circuit, where zeroing voltage sources looks like shorting them, because setting V equals 0 is the same as a wire. And zeroing current sources looks like opening them, where setting I to 0 looks like an open circuit, because no current flows in an open circuit. This is a super slick technique that lets you solve circuits very quickly, because the superposition subcircuits are often very simple. This technique of drawing, and we can see that by looking at the subcurrents we calculate, which are just found by simple dividers, and their sum gives us the same result. This technique of drawing multiple circuits to represent mathematical manipulations is a common tool that we'll come back to really often in this class. We do it because it lets us calculate stuff quickly by simplifying circuits to the point we can solve them in our head. So keep an eye out for it. We'll do this all the time, and it's a good trick. The magic of superposition can be explained by looking closely at a matrix representation of a linear circuit. On this slide, I've drawn a matrix equation that summarizes all of the voltage-current relationships enforced in the circuit. You can see an example by multiplying the first row of the matrix by this input vector, which will tell us that the value V should be equal to I1 times R1 plus I2 times R2 plus 0 times I. And that's the same equation that we got when we did our KVL loop around the left mesh on the last slide. There's a lot of depth in this matrix representation, and we're only going to glance at it. But just as a taste, this matrix is actually an adjacency graph, where the elements are showing the amount of resistance between 2 different nodes in the matrix. However, we are going to do one more in-depth manipulation to see where superposition comes from. By splitting this matrix out along the input vector, we can see that the I current source just creates one term in this matrix sum. And you could imagine that you could set I to 0, calculate the behavior of all of the other terms, and then set I to some value and calculate its effect separately from them, because the circuit is linear. So we can add or remove this I term at our leisure in order to make our calculations easier. This ability to analyze terms with a linear equation separately is really at the heart of superposition. So in summary, you can solve circuits with Kirchhoff's voltage law, Kirchhoff's current law, or superposition. You shut off supplies to make superposition subcircuits by zeroing them out, so current sources become open with I equals 0, and voltage sources become shorts with V equals 0. And superposition subcircuits correspond to subsets of the matrix representation of a circuit.